Hi, and welcome to Mr. Garofola's podcast. In today's episode, we're looking at example 4 from today's classwork, which was an introduction to piecewise linear functions. Specifically, we looked at the graphs of absolute value functions. And today was a busy day as we had a lot to do, and you guys did a great job comparing the graphs at the beginning of class toward the middle of class, and we got a lot of great characteristics out of that exercise. Hopefully those things will enable us to understand these graphs a little bit better, and we're going to be working more and more with them in the coming days. So in this example, we're given that g of x is equal to the absolute value of x minus 5, and we're asked to first evaluate for 3 input values, -3, 5, and 8. I'm pretty sure most of the classes had done this exercise, but just as a review, if we plug in -3 for x in the rule, we would have the absolute value of -3 minus 5, which would simplify to the absolute value of -8, which would be 8. You'd repeat this process for each of these. 5 minus 5 would be 0, the absolute value of 0 is 0. And lastly, g of 8, 8 minus 5 would be 3. The absolute value of 3 is, of course, 3. So this gives us a number of ordered pairs, actually 3 ordered pairs, in which we can plot on the graph below. So remember, in this case, y would be equal to g of x, since we're defining the function as g. So these values that you're getting here, your outputs, these are your y values, and your inputs are your x values. So we have the following ordered pairs: -3, 8, 5, 0, and 8, 3. So let's go ahead and plot those: -3, 8, 5, 0, and 8, 3. So we don't get too great a picture of the graph here. One thing we do know, though, from earlier in class was that these absolute value functions will graph as v-shapes. So it looks like we have some sort of v-shape going on, but what we're not certain of is where is the vertex. So is it turning like this, doing something like that? Is it turning on this point right here and then going up like this? Is it maybe going off in this direction and then turning over here? And this is only going to make itself apparent to us until we get some more values of x. So let's try some filling in some of the gaps in our graph. Let's start with x is equal to 6. We would have 6 minus 5, which is 1. The absolute value of 1 would be 1. I'm just going to replot that point. So 6, 1. We do 7. 7 minus 5 is 2. The absolute value of 2 would be 2. So it looks like we have the increasing part of the function down here. What we're really interested in knowing is this going to be the vertex, or is it going to continue on down in this direction? So let's try 4. 4 minus 5 would be -1, and the absolute value of -1 is +1. So it looks like we found our turning point. We have the V shape showing up right here with a vertex at 5, 0. Let's do a couple more points in between just to make sure we have the correct slope between these points. How about +2? 2 minus 5 would be -3, and the absolute value of -3 would be 3. So 2, 3 would be another point. Let's try 0. 0 minus 5 would be -5. The absolute value of -5 is 5. So we've got a pretty good picture. Go ahead and take your straight edge. And the graph of this function is indeed a V-shape with a vertex at 5, 0. So next, we're asked to rewrite g of x as a piecewise function. To do this, we'll need to break this graph apart into the characteristics that are occurring in both the decreasing and increasing parts of the function. So we see the decreasing part of the function here and the increasing part here. So the question for us is, for what x values is the graph decreasing, and for what x values is it decreasing? Well, notice as we move to the right of 5, we see the graph increasing. So the graph is increasing when x is greater than or equal to 5. I'm going to go ahead and fill that in down the bottom, because when we define our function as a piecewise function, we'll need to use that. However, when I go to the left of 5, you can see the graph is decreasing. So the graph is decreasing when x is less than 5. I'm going to go ahead and fill that in down the bottom as well. Now we need to define rules that cause this decreasing and increasing graph to occur. So we need a slope and y-intercept for each part. So for the decreasing part, we can use slope triangles. You can count down 1 over 1, down 1 over 1. The decreasing part has a slope of -1. The y-intercept of the decreasing piece is right here at 5. So we have a slope of -1 and a y-intercept of 5. On the decreasing part of the function, the rule would be -1x, or -x, plus 5. So we've just defined this piece of the function, just the decreasing piece. It has a slope of -1x plus 5 when x is less than 5. Now the increasing part is actually a little bit more difficult. The slope isn't too bad. Again, if we use slope triangles, up over 1, up 1, to the right 1, up 1, this has a slope on the increasing side of 1. The y-intercept, however, is not as apparent. If we look, the 5 is our x-intercept. The y-intercept of this graph, we would have to envision the line continuing down. It's going to strike the y-axis somewhere down in this area. So let's see what would happen if we extended this line. If I extended this line at a slope of +1, I would find that the y-intercept ends up being -5. So on the increasing part of the graph, the slope is 1, y-intercept is -5. So for our rule would be x minus 5 when x is greater than or equal to 5. Now, this was only there to help me. I'm not going to leave this. This is not part of the graph of the absolute value function. I'm going to move it on back to the correct turning point. I would suggest that you do the same in pencil. Draw it in, erase it back off when you're done because it's not part of the graph. So there, we've done it. We've now defined this function as a piecewise function. Here are the two pieces that we defined. So how does this graph compare to the graph of f of x equals the absolute value of x? Well, remember that graph looked like this. Had a vertex at the origin, a slope of -1 and +1. Here was the vertex of the original. Here's the new vertex. So it appears as if the vertex has simply been slid over to the right 5 units. And since the vertex moved 5 units, that means all the points on the graph moved 5 units. Now this type of transformation you learned in 7x is called a translation. The graph was translated 5 units to the right. I'm going to go ahead and take this off, as it just served the purpose of making the comparison. I'm also going to go back and take some of this information off so we can really see the graph a little better. So let's take all of this off. I'm going to leave those arrows on there because we weren't restricting the domain. All right, so now they're asking, what is the domain and range of this function? Well, the domain is unlimited again. We could put in any x value we want into this function and we'll come out with an output. So the domain, once again, all real numbers. Let's look at the range. Well, once again, we see this vertex is preventing any y values from going into quadrant 3 and 4. Remember, the values of y in quadrant 3 or 4 are negative. This tells us that the values of y must either be 0 or positive. So the range, y is greater than or equal to 0, or if you want to use interval notation, it would be 0 in a bracket, followed by a comma, infinity, and parentheses. Let's look at the rest of this example. In part F, they say, suppose the domain of this function was restricted. That means it was limited to the interval -1 is less than or equal to x, and x is less than or equal to 7. Draw the graph over this interval. So let's talk about what that means. When you think about restrictions on a domain, it's basically asking us to only use certain x values. And in this case, it's asking us to only go from -1 to +7. So think of these as walls. The graph may only appear within these walls, where x is -1 to +7. Nothing else about the graph will change. It still has its vertex at +5, 0. It still has a slope. Still has a slope of +1 on the increasing part. Pardon me while I change out my line here. And it still has a slope of -1 on the decreasing part. I'm going to go ahead and take away those walls that I built. Take them like that. And this is the graph of that same function over a restricted interval. To emphasize this, we use endpoints. Okay, this is an endpoint. This is an endpoint. This very clearly demonstrates that we're not considering any values beyond these points. So now it asks us, what is the new range of this function? Well, once again, we see that the y values are not going into quadrant 3 or 4, so it's positive y values. But the highest we can go up now is at this endpoint, and that has a y value of 6. So the new range of this function is that y must be less than or equal to 6, greater than or equal to 0. This is the highest we can go, and this is the lowest we can go. Everything in between is possible. Well, I hope this video was helpful for you. Use it to help you on your homework. If you encounter any major problems, please send me an email, and I'll see you in class.